We're going to cover lesson 8. This is absolute dating. And the thing you need to realize about absolute dating is with relative dating, you're saying, okay, the bottom layer is the oldest, the top layer is the youngest. But how old is that? Can you tell how old the bottom layer is just by saying it's the oldest? No, you can't. So absolute dating is saying the bottom layer is 65 million years old. So you're finding the exact age in millions or billions of years. Could be thousands too, I guess. But if you're doing absolute dating, you're finding the exact age anyway. Now, the simplest way to do absolute dating is to have something like tree rings. Okay, so tree rings, I'm sure you know, one ring is equal to 1 year. There's an equivalent to that in rocks. Those are called varves. And that's another method of determining the absolute age is by looking at varves. And those are sediments that show yearly cycles. They're commonly found in glacier lake beds. Each spring or summer when the glacier is melting, it's depositing just a ton of sediment in the streams. And you can tell the difference right here. So sometimes rocks will have layers to them, just like tree rings, and you just have to count them up. That's relatively rare, however. Okay. Now, most of the time, what people have to do is called radioactive dating. Okay, radioactive dating is a little more difficult. Okay, what we have in nature are radioactive things. Now, these radioactive atoms are kind of like a house that's too crowded. Okay, you get a bunch of people, shove them in a house, they're not getting along, and one of them might run away because it's just so much, it's so unstable inside of there, you could say. Okay, radioactive dating, how it works. In nature, there are naturally occurring radioactive elements. They decay at a steady, predictable rate. So that's what we're going to use to try to figure out the age of some things using half-lives. Now, what each person has on their desk, on what I'm showing on the screen here, is a bunch of carbon-14. Carbon-14 is how we date life that isn't alive anymore and see how old it is. Okay, carbon-14, you don't have a lot of it inside of you, but you do. It's a slightly radioactive element. So every 100 years, some of it might decay a little bit. Okay, so of all this carbon here, some of it is going to decay into something else that looks like this. So while you are alive, you have all this carbon going in, and you're eating carbon-14. Most carbon is carbon-12. That's not radioactive at all. But while you're eating, all the carbon, or at least most of it in your body, stays carbon-14 just because you're eating more carbon, eat more carbon. But then people die. I'm sorry to tell you. And you stop eating carbon. Now, over time, this stuff is going to decay at a predictable rate. This is the point where we look at the next page and we talk about half-lives. Now, the half-life of carbon, in this case, it's the time it takes for half of the carbon-14 to turn into nitrogen-14. So we know how long it takes for half of that carbon to flip from being all carbon-14 until it's half nitrogen-14. And that time period is called 1 half-life. So here's what that looks like. If we go back, okay. Now on your tables you should have a bunch of carbon. Over the next 5,700 years, that's the half-life of carbon, half of these carbons are going to turn into nitrogen. So in other words, right now you have 50% of your carbon remaining, or 1 half, and 1 half-life has gone by. So story time. A long time ago, in a cave, poor little Casper, the caveman, died in a cave, and so the cave became like a grave, and Casper's body is still there. Okay? Now, 5,700 years went by, and half of the carbon in carbon-14 in his body turned into nitrogen-14. Okay, so the carbon percentage is now 50%. That's half in fraction. One half-life has gone by. Okay, now over the next 5,400 years, half of the remaining carbon also flipped into nitrogen-14. Okay, so now you need to flip half of the remaining carbon on your table. Okay, here's what it looks like on the table I made here. We have 25% remaining. That's only 1/4, and we have 2 half-lives going by. If we keep this going, the third half-life, half of the remaining carbon will flip over again. You see that eventually you start running out of carbon to flip. You end up with 12.5% carbon remaining. That's 1/8. And we have 3 half-lives. Just to fill in the chart, 1/16 is next. And that's 4 half-lives. Now, to finish my story off with poor Casper, the caveman who died in the cave. Okay, we found him. We tested the carbon we found in him. We found that 1/16 of his carbon is still remaining. How many half-lives have passed if 1/16 of the carbon is remaining? Well, 4 of them have passed. Okay, if we skip down on the notes a little bit. Example. A skeleton is found to contain 1/8 of its original radioactive material. How many half-lives have gone by? So after 1 half-life, only 1/2 is still here. Okay, well, it's got 1/8, so we've got to keep going. After 2 half-lives, only 1/4 of that material is left. Almost there. After 3 half-lives, we are up to 1/8 is what is remaining. Okay, so after 3 half-lives, our skeleton has existed for 3 half-lives. Carbon-14 has a half-life of 5,700 years. Okay, if 1 half-life is equal to this, 3 times 5,700 is 17,100 years. So now our skeleton we found, that's poor Casper, found in the cave. Oh, that's Casper's dog or something. We can tell by doing this that he has been there this long. That's how long ago he died. What would make this answer a little bit better is the about symbol, because it's not exactly 17,000. We can't tell exactly, but we can still tell pretty close. If we look back up at this graph, the graph kind of shows what's going on here. The original carbon is sinking down by fractions. This one's climbing up. But you only can use carbon out so far before this line is just too close to 0. And you just can't use it. So maybe 30 or 40,000 years is what you can reliably use carbon for. That's why there are other radioactive elements that we can use. Okay? So we have rocks measured out in the billions of years. Okay? Well, that's because of our radioactive friends here. Okay? So carbon-14 works only in life. So only things that were alive and eating carbon and eating plants and stuff are the ones that have carbon-14. So you can't use carbon-14 on a stone tool or something that somebody made in a cave. That's 5,700 years. Okay? Sedimentary rocks, we can use potassium-40, which breaks into argon and calcium. Okay? That has a lifespan of 1.3 billion years. Last one is igneous rocks. That's uranium. This uranium has a half-life. It means half of it turns from uranium into lead in 4.5 billion years. That's about how old the Earth is right now. So one half-life of this uranium. Okay, so we already went through this. Okay, now towards the bottom there's some extra information. Carbon-14, just so you kind of understand what's going on there. Carbon-14 is a radioactive isotope of regular carbon-12. Carbon-12 is what we have in our bodies mostly. Most of our carbon is carbon-12. Okay? Its half-life is 5,700 years. It occurs naturally and is absorbed by all living things when we eat and drink. When we die, we no longer ingest carbon-14 and it begins to decay, turn into nitrogen-14. By comparing the amount of carbon-14 and the amount of nitrogen-14, we can determine how long it has been decaying and therefore when the organism died. It's only used in things that used to be alive. Right? Potassium-40 was the next one. We can only use it to find the age of sedimentary rocks. It's a half-life of 1.3 billion years. Okay? Last one, uranium. 4.5 billion years is its half-life. Though decay is the oldest rocks on Earth. What's interesting is that it's not reliable for rocks that are under 10 million years old. That's just not enough time to use uranium to date them. Okay? These are only in igneous rocks. So this is kind of a rundown of how we use radioactive dating to find the age of rocks.